Welcome back, Chemistry 30. This is the second booklet in Unit 4, 17.2, Factors that Affect Reaction Rate. So we'll look at examples of catalysts and inhibitors, identify the four factors that affect the rate of a chemical reaction, apply collision theory to account for the factors which affect the rate, explain the roles of catalysts in a chemical reaction, and interpret energy versus pathway diagrams like we did in the previous booklet for catalyzed and uncatalyzed reactions. So the first factor that we'll look at is the nature of the reactants themselves. So if you have your reactants in a simple form, so if they exist in ion form, so dissolved already, or if they're a easier particle, then the reaction rate will be faster than more complex reactants. Because with more complex reactants, you have to break them down first, then react them. Whereas these are already broken down. So for example, baby food is easily digested compared to adult food. You could use that as kind of a reason why. And some of the reasons there, of course, fewer collisions are required because the molecule is already broken down. So in terms of things colliding, collision theory, more collisions are required to break apart something that's more complex than something that has already broken down. All the energy can be used to help it reach the activation energy barrier. Now, for the rest of these, I did do demos in class. If you missed them, I do have, with the next video, I go through all of the factors, and you can see easily how they affect the rate. The first one was concentration. So if you increase the concentration of something, you'll increase the rate. And the reasoning there is that if you have more particles, which is what happens when you have a larger concentration, there's going to be more things colliding. And of course, if you have more things colliding, chances are more of them will meet the energy requirements to overcome that energy barrier, the activation energy. And if you look at the videos after this, you can see I do an example with that, using different concentrations of hydrochloric acid. Surface area. If you increase the surface area of something, you'll increase the rate. And if you look at the demo, I do that with cornstarch versus cornstarch blown through a tube. If you increase the surface area of something by making the particles smaller. So if you make the particles smaller, you're increasing how much area is exposed to oxygen and flame, therefore more collisions. And again, if you have more collisions, chances are more of them will meet the energy requirements. Temperature is the next one. Of course, you know if you increase the temperature, you increase the rate. Because higher temperature means more energetic collisions. The reactants are moving faster, hitting harder, so more of them will have enough energy to overcome the barrier. And of course, and the relationship there, it's not like the previous one. With concentration, if you double concentration, you'll double the rate. But with temperature, it's a little bit different. Initially, you'll have the rate will be a lot larger, but at higher temperatures, there's just a smaller difference. For example, if we have a small temperature versus a bigger temperature at T2 versus a bigger temperature at T3, if we use this as area under the curve represents the energy of the particles, and if this line here represents the activation energy needed to make a reaction, you can see here that at T1, only this many have enough energy. If we increase the temperature, things get shifted over to the right, and now we have this much, which you see in red. So it almost looks like double or even more. But at T3, a larger temperature yet, things shift to the right, but you can see it's only a smaller amount more that is able to have the right energy. So it's kind of a weird relationship there, just showing you that it's not doubling the temperature, you double rate. It doesn't quite work like that. Initially, when you increase the temperature, it makes a huge difference, but after a while, it doesn't. Catalyst, something that increases the rate of a reaction without being used up itself. And it does this by lowering the energy requirements. So you can think of it as lowering the hill, the activation energy hill, by doing a series of other reactions. We'll run into that more in 17.4. But for now, just think of it as lowering the energy barrier or lowering the energy requirements. So if we're to look at a graph here, the blue one represents a regular reaction. The red one represents with a catalyst, so it lowers the energy barrier. So more particles will have enough energy to overcome that area because it's an alternate route. So catalyst provides an alternate route which has a lower activation energy barrier. Inhibitor, it does the exact opposite. It raises the roof on energy requirements. So it decreases the rate by increasing energy requirements, making it more difficult for a reaction to occur. So the larger route requires more energy, so fewer particles will be able to meet that. And of course, in real life catalysts, we have enzymes in our body which provide an alternate route. For example, for digesting, we can only have a certain body temperature and you can only have a certain concentration of things. So we have catalysts in our body that help without reactions. And if you think of food preservatives slow down the rate in which food decays, so it lasts longer. So those are kind of practical examples there. One final thing here, heterogeneous catalyst versus homogeneous. Hetero means more than one different phase. So that means a catalyst, if all of our reactants and products were in liquid, I could have a solid catalyst, and that would be heterogeneous. Homogeneous, it means that the catalyst is in the same phase. For example, if they were all gases and if my catalyst was a gas, well, that works. And we have a few more diagrams here. We'll just skip to the back page. Looks something like this. So I have our regular reaction. I think I changed it up. Yours has E1, E2, so I kind of changed it a little bit here, so you have to follow along. So number 1 would represent the activation energy without a catalyst. Number 2 is the activation energy with a catalyst. So the requirements are lowered down. And I don't think I gave a 3 and a 4 here, so I just omitted that. 3, E3, it's the difference between here and here, so it'd be what the reverse reaction would have for an activation energy barrier. And 4, which I'm changing here, it goes over here, so that's the activation energy of the reverse reaction without a catalyst. And I added something which I called E5, which represents the pathway that an inhibitor would take you. So it's just, I kind of rounded a room here, folks, so you have to bear with me. It goes above the blue line on mine, so it raises the energy requirements there. Okay, so with the catalyst and without a catalyst. So the vocab here, just 2 things. Catalyst increases the rate by lowering the activation energy barrier, whereas inhibitor decreases the rate by increasing the energy requirements, so increases the activation energy barrier. Okay, I think that is it. So that's the end of 17.2. See you soon.